Chapter 9 has to do with some properties of right triangles. 9.1 has to do with some interesting relationships that exist between right triangles, similar right triangles. So let's take a quick look at this. Now we know that, from our talk in chapter 8, we know that we've got some relationships that tell us if two triangles are similar. We have some similarity, just like we had congruence relationships. What were the similarity relationships? You remember? What's one of them? Angle, angle, the easiest one. Yeah, angle, angle, and then we also had what else? Side, 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 and side, angle, side. Very good. So which is the one that applies here? Which of those three is the one that tells us that these two triangles are similar? Angle, angle. You got it. Okay, good. Okay, now what we notice here is that if we take, and I'm going to introduce a new, well, it's not a new word. We talked about it, but not very much. If we take a right triangle, so, and I'm talking about, in this case, we're focusing on the outside big right triangle. So this guy, triangle ABC, that has a right angle in it, right? Now, if we set that down on its hypotenuse, so if we rest that on a flat glass coffee table on its hypotenuse, then wouldn't you agree that the right angle is sticking up in the air, right? So that's the right top. Now, if we drop down what's called an altitude, which means we're gonna make a segment that's gonna go from this vertex that's sitting up in the air. We're gonna drop that straight down until it intersects the opposite side at a right angle. So this is our altitude. Okay, that green segment right there is the altitude. If we drop down an altitude, then it cuts that big right triangle into two smaller right triangles. Right? Aren't these both right triangles? Because we said that this has to be a right angle, right? Yeah. Okay, what's interesting about this is all three of those triangles, the original big one and the medium and small ones that we cut out by dropping down that altitude, are similar. And it's pretty easy to show that, actually. In fact, it's really easy to show that. All we need to prove that two of those triangles are similar is to show that two of their angles are congruent, right? So what if I were to take this medium-sized triangle and let's extract that from the big one? So let's draw it by itself. How about? So we'd have this triangle up here. It looks kind of like that, and that's triangle ACD. That's a right triangle. Okay. Are there two angles in the medium triangle that are going to be congruent to two angles in the big triangle? Well, one of them is pretty obvious. What's that? Okay, they share angle A, don't they? Right, so we can see right away that that's congruent to that. And then, what's the other one that definitely has to be congruent? Yeah, they both have right angles, don't they? So we got a right angle there, and we got a right, well, I just do it here. Right angle there, and a right angle there, right? Does that make sense? So those two definitely are similar. We could do the same thing with this little guy on the right also. If I were to pull him out of there, so let's pull him up there. Right? This guy has, so that's B, that's D, and that's C. What angle do they share? B. They share B, don't they? So B has to be congruent to itself. And then they're also both right triangles. So we can agree, all three of those are similar to each other, right? Okay. More earth-shattering than that is what we can do with that similarity. You thought you were done with geometric mean, but you're not. Turns out there are some proportions we can set up with these three triangles that we've created with this altitude. Okay? One of them is this. One of them says that if I consider the altitude itself, so this altitude that I drop down, that's going to be the in-between value, or the geometric mean, of the two pieces that it cuts from the hypotenuse. Okay? So it tells us this, right? CD in this case is the altitude, right? So let's color that green. And remember, when we have a geometric mean, remember how that works. The geometric mean is going to be the denominator of one fraction in the proportion, and it's going to be the numerator of the other fraction, right? Okay, so there's my geometric mean. And then the other two pieces what we call the extremes, but we don't even need to use that term. The other two pieces are just going to be, like I said, the two pieces of the hypotenuse that got cut by the altitude. So the original hypotenuse gets cut into the red piece and the blue piece, right? Well, the red piece is AD. So that's going to go with, it doesn't matter which one, that goes with one of the means. And the blue piece, BD, goes with the other. That always works. That always works. If we start with a right triangle, we drop an altitude down, it always creates that geometric mean relationship. So here's how that's going to get used. These are the kinds of questions you're going to get.
Oh yeah.
Yeah.
Why is there no bells today?
AP testing.
They're still doing that?
What is that? Oh, you know,
Advanced
testing
placement?
for people in AP.
You get college credit if you score well enough.
So why are there no bells?
So it doesn't interrupt their tests.
You know, three balls are gonna mess up the landing and
Yeah,
that beat is gonna
part of
mess
the
up
rules
the
for
beat.
AP. Anyway, that's neither here nor there. Okay, how would we solve for x here?
Multiply.
Yeah, what? Okay, nobody say anything yet. Everybody stare at that for a second. See if you can come up with, can we set up a proportion, a geometric mean proportion, that's gonna allow us. Okay, hold that
I'm
thought.
putting my hand down now.
No, hold on. Anybody else have an idea?
Can't you do the things that we've been doing? You know, like put X over 20 over 20? Like that? Yeah.
Okay, so we're gonna set up a geometric mean. Now, in that relationship we just talked about, right? We said if we drop down an altitude, it's gonna cut the hypotenuse into two pieces. So which parts go where? You always want to start with the geometric mean. That makes it easier. What's gonna be the geometric mean of those three? And look at the three things that we're trying to find here. This is the blue one, right? X. This is the red one, which we know is 12, and the altitude is 20. Hey, quit talking there, please. Okay, so how are we going to set this up? Start with the geometric means. What's the geometric mean? What's the middle value of all those?
Oh, BD.
Yeah, the 20 is, isn't it? Right? The altitude is the middle. And so that's the one that we can put on the bottom of one side and the top of the other side. That's what the geometric mean is, right? It doesn't make any difference which of the two, what order you put them in. But you just have to know what are the other two pieces that go in that proportion. Well, they're going to be the pieces of the hypotenuse that were cut by the altitude. So the x and the 12. And it doesn't matter if the x goes there and the 12 goes there or vice versa. Makes no difference. Let's just put the x on top. Doesn't really matter. And the 12 there. And then what would I do to solve for x?
Cross multiplying by.
Cross multiply.
Wait, so how come the 20s are opposite of each other?
Say it again.
How come the 20s are opposite of each other?
Because that's how the geometric mean works. Remember, we did some stuff last chapter where if I wanted you to find the geometric mean of, say, how about if we did geometric mean of 2 and 32, right? There's a formula for that, but rather than the formula, remember what I told you to do here. The geometric mean, if we call that x, the geometric mean always just looks like that. Bottom of one side, top of the other side, and the two numbers that we're taking the geometric mean of just always go opposite the x, right? And if I cross multiply, I just get x squared equals 2 times 34, which is 64. So what's x?
Eight.
8.
I knew that. You heard me.
Okay.
Yeah.
So 8, that's how we get it, right? That's the geometric mean. Well, that's what we're doing here with these problems too, right? We got the geometric mean, we're going to write first, and then the other two pieces, take the other spots in the proportion, and then from there on out, you guys are pros at that. We've done that a ton now in chapter 8. Solving proportions is easy. You just cross multiply and get 12x equals, what? What's 20 times 20? Yeah, 400. So then if I divide both sides by 12, what do I get? 30,
Two.
let's see, 12, 30, so we can get 40 again. So it's just going to be 33.3 repeating. So that's what I get for my, for x. Does that make sense? You always want to ask yourself,
real quick, there's a way. This doesn't guarantee you got it right, but it can, in some cases, it can guarantee you got it wrong. 20 should be the middle value between x and 12. Not the average, right? Not the exact middle, but it's got to fall in between those two. Does it? Yeah, it does, right? 20 would be in between the 33 1/3 and the 12, right? So there's a good chance, and we did get it right. Okay. Make sense?
No.
Okay,
Let's learn that in 22 now.
we're good?
Yeah, I was gonna say, what's up your budget?
Okay, so another one that comes up. Okay, there's really just one other geometric mean relationship, and you can, they're gonna break it into two separate equations, but we don't need to. I'll show you why here in a second. Here's the other one. The other one says if you take one leg of the original big right triangle, it doesn't matter which one. In this case, we're going to take the short leg. And everybody agrees if I take my original right triangle up here, what do I call side AB? Obviously, you've already told me. What do I call that?
False. That's hypotenuse.
Hypotenuse, right? That's the hypotenuse. And then the other two sides in a right triangle are called what? Legs. Okay, so if it's not the hypotenuse, it's a leg. Okay, so here's what this other one says. The other one says that if we take one leg of the original, okay, I'm gonna ask one more time. Stop talking, please, over here. I keep hearing talking. It's messing me up. So it's gotta be messing them up. Okay, last time I'm asking. If we take one leg of the original right triangle, that's going to be, now this one's a little more complicated. It's going to be the geometric mean of the whole big hypotenuse and the smaller piece of the hypotenuse that's right next to that leg. Okay, so CB in this case, that's green, right? That's our green segment, is going to be the geometric mean of the whole thing, AB, and that little short piece of the hypotenuse that's right next to the leg. Okay, make sense?
Yup. How does those correlate? Like, I mean, like before we said that like DC is in between A and B, or AD and DB.
Mm-hmm.
Just I don't know.
Well, you can see now. You can.
Easy. You know what I mean? Because it was just like that, so it's in between.
Right. Well, this one's a little harder to set up, but you can see visually that it's still going to work. What if I make this a hinge right here, right? And I let this piece kind of fall down. Would you agree this piece is going to kind of fall down and hit right there?
Yup.
Right? So the length of CB, you can see up there pretty clearly that it's going to be in between, somewhere in between the whole hypotenuse, the red segment and the blue segment. And so you can kind of see that, yeah, it looks like it ought to work, and it does. Let's look at a quick example. And then the other one they give you is just the same deal, except opposite leg. Okay, so what about this one? This one's saying if we take the other leg, the longer leg, AC, the longer leg AC should be the geometric mean of what? Once again, what's the leg of the big right triangle is the geometric mean of what two things?
AB.
Okay, well, and more generally, the whole hypotenuse, right? So AB, and the piece of the hypotenuse next to the leg. When I say piece of the hypotenuse, everybody gets what I mean, right?
Yeah.
Remember, the hypotenuse is in the big right triangle is the one that's been cut by the altitude into two pieces. So in this other relationship, the altitude doesn't play much of a role. All it's really doing is just cutting that hypotenuse into two pieces because we need to use one of those pieces in our proportion, right? That's all it's really doing. That the actual altitude itself never shows up in the bottom two cases, does it? Right? But you see what we're getting at. Okay? So, how would we do this problem? I want to solve for x. I know this is an example I can see right now. I've got a right triangle that's been cut by an altitude. So we kind of know right away that we're trying to set up a proportion using a geometric mean.
X over 20, 20.
Okay, start with the geometric mean. What's the middle value? What's the geometric mean in this case? 20. The leg, right? So the 20 is the geometric mean, and then the other two pieces, you just got to make sure what they are. So that's the leg is the geometric mean of the whole thing, the whole hypotenuse, and the piece of the hypotenuse that's next to the leg. So it's just like that, isn't it? Right? But what do I do from there? Cross multiply. Okay, cross multiply and get 25x equals what? 20 times 20? So x equals 16. There you go. And does that work? Let's check. Is 20 in between 16 and 25? Yeah, it is, right? Okay. Make sense? It's not, but it's not supposed to be. It's not supposed to be the average. It's the geometric mean, which is a little different. Right? It's not going to be in the middle of the two. It's just going to be somewhere in between them. That's kind of our check. Well, it's true. Okay, I think we're done. 2:05.